Okay, so welcome. Welcome to this lesson, the second lesson of the course Applied Acoustics for Sound Reinforcement. This first part is dedicated at the generical and theoretical acoustical contents that I want to present in a form of in memory of Professor Angelo Farina, who recently passed away. I learned so much from Angelo, from Professor Farina, and I gave him permission in the past to use his materials. Therefore, this video that I'm publishing on my YouTube channel will recall or contain his material, his informations, also his way to do a lesson, okay? Uh, at the best of my possibilities, obviously. So, uh, in future, I want to publish all the exchange of the ideas that I had with the professor. So thanks, Professor Farina. So the topic of this lesson are to the physical quantities used in acoustics to define the sound field and how to evaluate them with the decibel scale, so the decibel scale. The quantities of sound field are, and sound in general, that we can describe are these five. No? The first two are so-called field quantities that are related to the characteristics of particles of the medium. No? The other three are instead energetic quantities related more to the energy aspect of sound phenomenon, to the energy that travel in the medium or that stay in the medium in space. So you have to to think that if you look at any applied acoustic textbook from the 19th, you won't find energy quantities named, okay, in the book. They are therefore a recent definition in acoustic. So the first two quantities are field quantities, as I have said. Sound pressure um, and particle velocity. Sound pressure, attention here, is not the total air pressure in the medium, the air pressure we listen in general, but the deviation of the instantaneous air pressure values from the constant steady air pressure that is, if you remember the first lesson, 1 bar, 100,000 Pascal. The steady pressure is in practice the DC component, no? The sound pressure instead, the variation of pressure, is the AC component, the alternating component of sound pressure. Particle velocity is the velocity of particles, as the name say. Remember the first image, no? The image of the tube and the wavefront that move in the pipe, and the particle movements of the red particles, no? That you have seen in the previous in a slide of a previous first part. Particles moves locally a few millimeters, if you remember. And velocity of particle, this velocity of particle, the velocity of this movement is imposed by a moving surface, the cone of the loudspeaker, for example. Being air an elastic medium, when power pushed the surface, the cone, this movement compressed the near air to the loudspeaker layer, so we have more pressure in this zone. When cone retry, pressure reduce. Velocity is important for human perception in terms of spatial informations like stereo image, localization, stereo separation, source width. Um, Pressure is a scalar quantity and velocity is a vector. And so being a vector, it has three Cartesian components, no? So actually are free velocity, no, not one, okay? We have Vx, Vy, Vz. This is why if you want to record the sound field, the complete picture of the sound field, you need to record with a four-channel recorder. Okay, one channel for pressure and the other three for the velocity. And this is the principle we will apply in the in present course using ambisonics microphone. To define the sound field, we need also energetic quantities for an energetical analysis of the sound field. We define these quantities with some average value in time, okay? Field quantities instead are called instantaneous quantities, sampling them many thousand times per second, no? The sample rate, for example. In the past, computers were unable to store and process these large numerical quantities. Instantaneous data needed for acoustic measurement of field quantities. So energy quantities was created because average means to manipulate data less huge. Okay. Their use continue even today in the era of powerful computer. They are become a standard. What we listen in the sound field are just the field quantities. Attention here, okay? And we can only indirectly derivate energetic quantities. Sound energy density, sound intensity, energy. These are quantities that are strictly related to the medium. Sound energy density is the energy per volume, so joule per cubic meter. Is the density of energy trapped in one cubic meter of volume. Okay, the sound trapped in a unity volume. Sound intensity instead is a sort of a moving energy concept. So energy passing through one square meter of surface in 1 second. Okay, so it is measured as joule per square meter. It is associated to sound propagation. So when you are indoor in a closed space, a room, no, a theater, a cinema, the relevant quantity of the sound field is the sound energy density. Okay. When you are outdoor and sound is free to propagate, the relevant quantity is the sound intensity. So Physically speaking, the sound experience is different outdoor and indoor. Also for energy density and intensity, we have in total four quantities, not two, because energy density is a scalar quantity. Intensity instead is a vector, so it has three components. Again, in Ix, Iy, Iz. Sound power is a quantity that is not measured in a sound field. Okay, uh, and in this is different from the other two energy quantities we have seen, no, density and intensity. It is not measured the power at a receiver, but like the others, but it is strictly related to the sound source, voice, human voice, speaker, machine, etc. A power source that produces sound emitting a number of watts in the medium. Sound power is the cause we can see, no? The other quantities are the effect. Sound power is a time average value. Consider that the human voice is just 1 milliwatt as power, okay? A loudspeaker emits low levels of power, 0.8, for example. 1 watt loudspeaker is very loud, consider this, okay? A commercial loudspeaker transform in sound power a very low percent of the electrical input power, watt, no? The watt that you input in the so-called efficiency of the loudspeaker, no? Most of the energy instead is transformed in it. So the powers involved in listening experience are very small, and our hearing system is incredibly sensitive to these minimum variations of pressure. A speaker converts so the electrical power in acoustic power, the pressure waves. It is possible to control the level of power with a knob. The pressure level is produced by the power level. It's a good practice to design a sound system that produces the desired pressure level, LP, with the less possible power level, so consuming less watt as possible. Power level LW represents the global sound energy that the source irradiates in the room, in the medium, and it is global. Pressure levels instead are local. Pressure is local, is related to the specific position and describes what happened there. Okay, in this set or in this another set. Uh, Physical laws relate these quantities according to a cause-effect relationship. For example, we see here the relationship between pressure and velocity. Their ratio is called acoustic impedance and describe the impedance of the sound field, not of the medium, because it depends by the medium itself and by the curvature of the wavefront. It describes the medium in the case of the theoretical case of the plane wave, like in the PEEP you have seen in the first lesson. And in this case, is given by rho zero multiply C0, the velocity of sound, where um, RO, R0, R0 is the density of air that is equal plus minus 1.2. In reality, wavefronts are often curved. We will see this later in the course when we will talk about the sound propagation. The unit of air impedance is rail. Air impedance value is something like 400 rail because we multiply 1.2 kilogram per square meters and the velocity of sound in normal condition that is 340 meters per second. In real world propagation is more complex the situation, okay, than the plain case. It is really difficult in real world to measure impedance in air. The only way is to record pressure and velocity with a sound field microphone. With for example, an ambisonics techniques. So you measure the pressure and the three components of velocity. The problem is pressure values are positive and negative because the oscillation up and down the steady pressure. So if we average linearly all the pressure values, we get zero. When the waveform is complex, a linear average of the amplitude of the signal becomes ambiguous, and the use of a maximum instantaneous values is not more representative of human perception. So we need to make not an average of pressure, but directly, but an average of the energy associated to the pressure. Compressing air is like if you compress a spring, creating a compression in which you trap energy that is proportional to the square of the pressure. Okay, it is the potential energy. The same for velocity that is associated to kinetic energy that is proportional to the square of velocity. So we do a quadratic average of the field quantities, and these give an energetic meaning to the field quantities. So for pressure, we define the so-called RMS, root mean squared value. The same for velocity. So you practically take all the single instantaneous linear values that are positive and negative and square them. Okay. You sum all the instantaneous linear values squared, no? And then you do an average, a linear average of this value. So total squared values over n values, the number of all the values, all on the square root. Okay, so you in this way obtained the efficient pressure or efficient velocity that is called also PRMS, VRMS. I hope it is clear. Okay. Energy density is the energy trapped in 1 cubic meter of volume. So it represents the total energy in the room. We used we use squared quantities and RMS values of pressure and velocity to calculate the energy contained in the medium, the density. Because the kinetic energy is proportional, to the square of velocity, okay? Kinetic energy, and potential energy is proportional um, to the square of the pressure. In this way, I convert the field quantities in energy quantities, the velocity in kinetic energy, the pressure in potential energy. Total energy density trapped in a room is equal to kinetic energy plus potential energy, and it is joule so per cube meter. Energy density is very important because with this is defined the reverberation time, for example. No, with this we evaluate if a sound is strong or weak, etc. Sound intensity I no, measure the flux of energy passing through a surface. So it is not more the energy trapped inside a volume, is the energy that is passing through a surface. Exactly the energy passing through the unit surface in 1 second. So watt per square meter. Sound intensity is a vectorial quantity which has a module, and direction, and a sign, a verse. The formula is pressure, that is a scalar quantity, multiply velocity, that is a vector. So the vector intensity aligned and parallel with the velocity vector transport in the energy field the vectorial information of the particle velocity vector. Attention, we don't listen intensity, we listen density. Okay, in the theoretical case of the plane wave in the pipe, in the tube, no? Intensity is equal at the product of density multiply the velocity of sound, C0. So more the wavefront becomes plane, no? Less interaction they have with the boundaries with the room, and so intensity is d density per velocity of sound. In the reality, we have reactive rooms. We have quite always interactions with walls, with boundaries, with the room in general. Sound produces reflection, and the wavefront are curved. Okay. In these cases, in reality, the intensity is always less than the product density per velocity of sound. We can describe a ratio between intensity and the product density multiply velocity of sound, which is C0, the so-called RE, that is equal to intensity over density per C0. So this ratio is 0 in the case of standing waves in a room, or in the case of a reverberant field in a room where energy does not propagate, but stay. Okay, it remains stationary in the room. And this is what happens in truly reverberant Sabinian environments, no? Where the energy of the reverberant field is equal at every position, at every listen position. Take a look at my video on reverberation and misconceptions about reverberation. Sound power. Sound power describes the capability of sound source to radiate sound. It is measured in watt W. It is not possible to measure directly the radiated sound power. Hence, an indirect method is employed. Let's imagine to create a cage of metal around of wires, no? That delimit sections um, around the sound source. A machine, for example. It is as if we were creating a surrounding surface called envelope surface. On this surface, now I can calculate the vector I, the sound intensity. The sound power emitted by the sound source is given by the surface integral of the sound intensity I. So if we divide the total surface in a number of n elementary surfaces and we measure separately the sound intensity which with the intensity probe on each of them, the integral becomes summation of all the multiplications of the surface area of each section with the intensity measured in each of these. Is valid also the inverse formula, so we can obtain intensity from the ratio between power and the surface. So intensity is equal at power over surface. So if we take the example of the theoretical point source, no, we have this, the point source with array that I consider for my surface listening distance in this case. Okay, surface is equal at 4p. Oh my God, I remember right? Yes. Radius squared radius. Okay. So intensity becomes E equal to watt over 4p squared ray, the distance, no, of the receiver from the theoretical point source. If we consider this, I can outline a first formula for spherical propagation, no, in a free field, calculating the intensity at a certain distance. Having calculated the intensity, we can now calculate the density. That is the quantities that in reality give me information on how loud is sound. So if you remember how to cancel these scenes, so remember that RA is equal to intensity over d per T0, the velocity of sound. So if in the theoretical case of a plane wave, etc., consider RA, RE equal to 1, we can obtain so RE is equal 1, delete this. So D go here. We have that the density is equal at intensity that we have separately calculated before over C0, the velocity of sound. Okay? So the decibel scale that we use to manage these quantities. That is the second protagonist of this lesson. Decibel, it is not a measurement unit. Decibel is not the measure of sound directly. Decibels are a logarithmic scale with which we can define any physical quantity. There are decibel for pressure, but there are also decibel for temperature, for force, for velocity, for acceleration, everything. Everything can be described as with the scale of decibel. The physical quantities related to sound amplitude have a huge dynamic range between the, the hearing threshold and the pain threshold. Hearing threshold is for pressure 20 micropascal. The pain threshold is 20 pascal. A lot of range of variations. Okay. The human perceptions in reality compress such wide dynamic ranges in a much lesser variable perception. Okay. For this reason, a logarithmic scale is used in which the value of the quantity under examination is equal to the common logarithm base 10 of the ratio between a measured value and a reference value. Okay, the advantage of using a logarithmic scale is to linearize, okay, the perceived lewdness, making the number mapping linearly the human perception. In acoustics, we use 5 levels in decibel. A value expressed in decibel is called level. Okay, so we have the sound pressure level, the particles velocity level, the sound intensity level, the energy density level, the sound power level, and each of them have its reference value. Okay. You must understand also that the decibel scale has no meaning alone. It has a meaning of energetic scale. The ratio must be the ratio of two energetic quantities. For this reason, pressure and velocity that are not energetic quantities must be squared in the formula. Instead, intensity, density, power are yet energetic quantities, so are not squared in formula. You don't need to square a quantity that is yet squared by self, okay? When a square, I design, when a square is present in the formula for the properties of logarithm, you can extrapolate this this exponential value out, and 10 log becomes 20 log the ratio. Okay. Mathematically is the same thing, but pressure is not more squared. And so you lose the physical meaning of energetic scale. So I don't suggest this use, okay, of logarithms properties. Why 10 log? Why the 10? So, because it's a decibel, as the word itself say. Mr. Bell originally used the bell. The bell is a bit too coarse as value, too large. 10 decibel is a huge variation. Is 10 times the energy. 1 decibel instead is near to the human perception threshold. Okay, a variation of less 1 decibel is not detected by humans. Decibel scale is always positive and start from zero. That is in reality the threshold of hearing. Remember, 20 micropascal, so not an absolute zero value. At as last slide, this and concept. This image show the correspondence, no, between decibels and noise. So the typical values examples of sound pressure levels. dB scales range from zero, as that is the threshold of hearing, to 120, 150. That is the threshold of pain. Okay, and so you can see some example of sound pressure levels uh, in dB for example, truck noise, urban, suburban noise, etc., rock band noise, etc. So I hope that all is clear. Thanks for watching. We will see for later for the lesson number 3. Okay, stop and stop.